Today we are walking through the paper titled Image Generators or Generalist Vision Learners.
Start with the main idea.
The paper asks whether a strong image generator only makes realistic pictures, or whether its training also builds reusable visual understanding. The authors test that by turning Nanobon and a Pro into Vision Banana and asking it to solve perception tasks.
Why was that still open? Generators already seem to understand scenes when they make images.
Earlier work showed promising zero-shot behavior, but the generated mask or depth maps often did not follow a format that could be decoded and scored reliably. Other strong systems added special modules or full task-specific fine-tuning, which helped one task but weakened the case for a single generalist model.
So the question is not just whether it looks plausible, but whether the output can be measured.
Exactly. Their move is to make perception look like image generation, but with strict color rules. The model receives an image plus an instruction, then generates an RGB visualization that can be decoded into a mask, a depth map, or a surface normal map.
What changes during training to make the generator follow the strict color rules?
Vision Banana is made by lightweight instruction tuning. The authors mix a small amount of formatted vision task data into the original Nano Banana programming mixture. The goal is not to rebuild the model for each test. It is to teach the existing generator how to express its answers in measurable RGB formats.
What kinds of tasks are included in that test?
The paper covers two broad groups. For 2D understanding, it tests referring segmentation, semantic segmentation. For 3D understanding, it tests monocular map-like depth and surface normal estimation. It also checks whether the model still performs image generation and image editing after instruction tuning.
Before we go into results, what does state-of-the-art mean here?
Here, state-of-the-art means the best reported benchmark performance among the compared methods. The important point is that Vision Banana is compared against specialist systems, not just against weak baselines.
What does the 2D segmentation evidence show?
For segmentation, the model generates color-coded masks. On Zitscape semantic segmentation, Vision Banana reaches 0.699 MIOU, while SAM3 reaches 0.652, so Vision Banana is 4.7 points higher. On ResCOCOG, it reaches 0.738 CIOU, slightly above SAM3 with Gemini 2.5 Pro at 0.734.
Does it win every segmentation case?
No. Instant segmentation is the weaker case. On SACO over the sampled queries, Vision Banana scores 0.540, while DINOX scores 0.52. The useful takeaway is more specific. The generator-style interface is strong on several zero-shot segmentation tasks, but separating many same-class instances remains harder.
What makes the fearfound text segmentation result different from normal category segmentation?
In fearfound referring segmentation, the prompt can describe appearances, actions, unusual object roles, or multilingual text. That matters because the model must understand the query before drawing the mask. The paper used examples where Vision Banana segments a stretching cat, a person described by clothing, and text appearing in more than one language.
How do they turn depth, which is a real distance, into an RGB image?
They first bend the metric depth values so nearby distances get useful resolution, then map the bent value along the edges of the RGB cube. Because the mapping is invertible, the generated colors can be decoded back into metric depth values.
Put the actual depth equation on the board. What quantity is it defining?
This equation defines a normalized curve distance from the real map with depth. The input D is the depth in meters. Lambda controls the curve shape, and C controls the scale. The paper uses it so a finite RGB color can represent an unbounded real-world distance.
What does the depth benchmark say after decoding those colors?
Across the shared depth anything V3 comparison set, Vision Banana averages 0.929 on delta 1 accuracy, while depth anything V3 averages 0.918. Across the full table, Vision Banana reaches 0.88 to average delta 1 and 0.116 absolute relative error, without using camera intrinsics during training or inference.
Why is the no camera intrinsics detail important?
Camera intrinsics describe the camera geometry. Many depth specialists depend on them to reduce ambiguity. Vision Banana instead relies on visual cues and object scale priors learned by the generator, so the authors argue it can infer absolute scale from a single ordinary image.
Is surface normal estimation handled with the same kind of complicated color curve?
Surface normals are simpler to encode. Each pixel stores a direction vector, and the vector components can map directly to read, green, and blue channels. The paper uses camera space normals, so left, right, up, down, and facing camera directions become different color components.
What does the normal estimation comparison show?
On the indoor average, Vision Banana has the lowest mean angular error at 15.5 for 9 and the lowest median error at 9.300. The visual comparison also shows finer surface detail than Lotus do in the examples, although the outdoor virtual KITTI numbers are slightly better for Lotus 2.
Does the instruction tuning hurt the original image generation model?
The reported generation checks suggest it largely preserves the base ability. Vision Banana gets a 53.5% win rate against Nanoban and a Pro on text-to-image generation, and 47.8% on image editing. That is close enough to support the paper's claim that the tuning unlocks perception without erasing generation.
What should viewers be careful about when interpreting the result?
The result is strong. The paper itself notes that image generators have higher computational overhead than lightweight specialist models. It also leaves future work for multi-view inputs, video inputs, broader task coverage, and tighter integration with language models.
So what is the final takeaway?
The paper's central evidence is that a powerful image generator can be lightly tuned to output decodable RGB answers for many perception tasks, and then rival or beat specialist models on several benchmarks. That supports the idea that image generation pre-training can act like a foundation for both creating images and understanding them.
That makes the claim much more concrete than just saying the generated images look smart.
Exactly. The key contribution is measurable visual understanding through the same image generation interface. That wraps up this paper walkthrough.